My talk is about intuition. I think that this is very important in general and in power electronics in particular. Okay, so what I'm trying to do in this presentation is really to look at what is intuition in power electronics. I'm not going to talk that much about power electronics, but rather how to use or how is intuition interlaced with the power electronics work. Will it be teaching, studying, or practicing engineering in power electronics? Here is what I'm going to talk about. First of all, I'm going to trying to define what is intuition, and then go and probing into intuition in teaching, students studying, practicing engineer, and in research. And I'm going to do an exercise here to track back a work that I did and to sort of try to find out where intuition came into it and how did it help to reach whatever goal was the objective there. And finally, I'm going to talk about whether intuition could be wrong, and indeed it could be wrong. So, and the question is, what can we do in order to not be in error? There are many examples here, and I understand there are a number of undergraduate students watching this presentation. So therefore, I've made these examples undergraduate student compatible. They are simple examples. By no means, the intuition is not restricted to simple cases, obviously. And this is just examples that I'm giving. So first of all, I'd like just to say what is intuition, just to give an example. Now, we are honored to have Professor Kolar attending this webinar. And I'm showing here is the Vienna rectifier, which, as far as I know or remember, it was actually invented while he was a student, a master student, I think, which was like 1993. I guess it was patented. And since then, it's been used by many, modeled, analyzed, studied, implemented in many units in industry. This is one of the most known circuits in power electronics, I would say, and useful unit, not just, there are some very well-known topology, but they are not used that much. So that's not the case here. So even so, I think there is sort of, or there was a sort of a fog on this topology that it's not very clear how does it work. I mean, yeah, you can analyze it, you can write equation, and here I'm showing, well, here the CPES contribution. You can do a space vector presentation. You can do a state space presentation. You can do a flow, a signal flow. But how does it really work? I mean, it looks like a complex thing that it's not exactly clear what it works. Well, Professor Kolar has a three-phase brain, and he can see immediately what's going on, but we humans don't have it. So the other day, I was sitting down and looking at this rectifier in connection with the project, and then by what I would say is pattern recognition, which I'm going to talk about, it's a part of intuition, I realized that there is a hidden boost here. And this is a bidirectional boost, okay? It's a bidirectional switch so that when the input, there's no rectifier here, and when the input is positive, then you have a positive output. When it's negative, you have a negative output, so you have a high voltage peak to peak here. And this is something that actually I've been using some years ago in connection with some laser converter. And so it's a boost converter. So, and also if you look at it with another configuration, which you can present the Vienna rectifier, well, I'm talking about the old two transistors rather than the new bidirectional device. And then, of course, you can see very clearly this boost. And then if you have this boost, and for one phase, and you add a boost, this bidirectional boost for the second phase, and then you add it for the third phase, here it is. Now there is a line here, which you don't have in the Vienna rectifier, but this line, because this is a three-phase system, doesn't carry any current, so you can just cut it out, and here it is. So here, by sort of recognizing the basic cell, you might say, inside, you can come up with this explanation. Well, it's like any other explanation. I'm not saying it's better, but it's different, and it's more intuitively understood. So you can see what's going on. You can actually control each one of these boost converters independently as a single-phase unit. So this is what I mean by intuition in power electronics. So let's go back one step back and say, what is intuition? And here is what usually is considered to be intuition. Intuition is a subconscious ability to understand or know something immediately without actually relying on conscious reasoning or step-by-step analysis. So intuition is something that pops up subconsciously as you handle something or you look at something. And another feature is that you can't turn it off. Well, you can decide that next week you're not going to dance or drink beer or whatever. You can't turn off intuition. If you look at something, then it sort of pops up, and you don't have to use it, but it's there. Okay, so this is the ability of the human brain to bring up actually previous experience related to what you're doing now. And I'm not a brain researcher, but I think there's a lot to study there, what is really going on with this intuition. Now, intuition in power electronics is very important because it's the ability to understand, predict, design circuit behavior through conceptual visualization, which is based on prior experience. This is the key here, and without relying on rigorous analytical calculation. Now, nobody is born with the intuition power in power electronics or in other things. This is something that is gained throughout the year, through experience, and it is very useful to understand things in a more general way, more physical way. Now, how is intuition exercised in power electronics? So I have here what I call the toolbox of the intuition. First of all, and very important, is pattern recognition. This is something that I already said when I showed this example of the Vienna rectifier. And that is to recognize topology, current direction, voltage polarity, energy flow. Once you look at the circuit, you say, aha, this looks like a buck, this looks like a boost, this is this, and here is the current coming from here going there. So this is a very important tool of this intuition ability. Another one is physical reasoning. That is to think in terms of not the equation or state space equation, but rather in terms of the magnetic energy, the flow, charges, and not equations, which you can later on, of course, build on your basic understanding. And then there is the mental simulation. That is that you sort of in your mind say, okay, this transistor now is turned on, the current will go this way, then go into the diode, etc. And by this, you understand what is really going on with the circuit without actually writing sets of expressions there. And then modeling, approximating modeling, using simplified equivalent circuit and rather than the mathematical derivation, that is to look at the average behavior of the circuit rather than the individual pulses going into the transistor back and forth, but just on the average, how does it work? And last and not least is the experience-based insight. That is, you build this ability by experience. Things that you've seen, things that you've heard, and this is then incorporated in the intuition that one has. So now I'm going into specific issues of areas in where intuition in power electronics is very important in my view. And first of all, it is teaching. And then studying, that is from the student point of view, and then the practicing engineer, and then research. Last in this is the question, how can we actually develop and improve the intuition? So let's talk about teaching. I think that it's very important for teachers, professors, to help students, first of all, to understand the material by intuition. That is to explain, first of all, things in the general terms, in the physical terms, rather than jumping into lines and lines and lines of matrices and equations, okay? And then it is also, I think, the duty of the teacher or professor to develop intuition by the student, because this is the tool that they're going to use in their professional life, and it has to be cultivated from the very, very beginning. Now, how can this be done? First of all, is this toolbox that I've mentioned, all these possibilities of looking at the circuit or a system or a control or whatever in power electronics, and then explaining things, first of all, in an intuitive way, and also to challenge the student to explain things by simple, basic physical processes rather than examining them whether they know how to solve the equation of a certain circuit. And then, very important, is to link what you're teaching to something that has been taught, so that the student will build sort of one on top of the other, a chain of knowledge that can then draw information from all these stages. So here are some very simple things that I've been using, and I'm just sharing it with you. That it's really simple-minded, but I found the students are really benefited from that. For example, what happens, to ask the student and to later on teach them, when you have an inductor with a current flowing and you short it? You'll be surprised. I've been asking this question. Many engineers, they didn't know exactly what is going on. And that's very bad, because this is a very fundamental thing that has a importance in many situations, not to mention, I don't know, phase shift converters, etc. So this is something that should be done at the very, very beginning. Another example is for the same inductor, what happens if the switch is open? Well, we understand the IDT is high, going to have a voltage, but what is the polarity of the voltage? Is it going to be positive here or negative here? Well, you can bring in the right-hand rule, the left-hand rule, etc. But the intuitive way is to say, well, suppose you have some conductance here, so high resistance resistor. You open the switch, current is flowing this way, then obviously this is plus, that's it. Now, what is important is not to remember that this is the situation, but rather to remember the process that is causing it. Because if you just remember that it should be, if the current is going out, it should be plus, then you can't do much about it. But if you understand this process, then you can use it in the case of a diode starting to conduct in some other situation. And here is a little bit more involved example, and that is the Chuck converter, okay? Well, to me, when I look at it, the first thing that I see, and I think many professional, power electronic professionals who see it immediately also, that you can say immediately what is the voltage on the capacitor, okay? Because the average voltage on the inductor is 0, or volt second 0 in steady state for one cycle. So here it's V in, here it's V out, so we know what it is. And then as you look at it, you see immediately that this is actually a boost converter, okay? Here it's turned on, you show this, the inductor, and then you see here, this is like then the load. So you know what is the transfer function. And then here it is clearly a buck converter, although the negative voltage here, because you're now feeding here this side, so it has to have a minus. And here we come up with the transfer function. Again, this is not the end of the story. Then you have to go into all the details, which is fine. But once you do this, then the students can really appreciate what is going on, understand it, and not to get sort of a little bit frightened with all this complex and that many components and units here. And this, due to shortage of time, I'll have to stop here and go to the student point of view, student side. I think my advice always been to the student is that you have to understand the circuit. It's not enough to be able to solve the equation. You have to understand what is going on. And this will be the first thing. And if you don't understand, ask. And what I'm giving an example here is a buck converter, in things that should be understood is that the operation is really based on the fact that you have here an average voltage. Although the voltage is pulsating, the average voltage is V times the duty cycle, and then therefore, again, because the average voltage is 0, it is equal to the output. So this is the transfer function. But it's more important to understand what's going on than memorizing this transfer function. Because again, if you just memorize it, you can't do anything with it later on regarding other units. While here, this is a tool that you got that now you can analyze other circuits. Another advice that I always have to been saying to my student is that you should always ask why. Don't be satisfied with sort of seeing something and that's it. Try to poke into it and say, well, why did this and why is this happening like this? And here I'm going back to this example and just say what, or just explain what I mean by that, by this why this exploration. We understand that the output is related to the input through this duty cycle. We are talking about open loop here, and that and this is when we assume that the average voltage across the inductor is indeed 0 during a switching cycle at steady state. That's fine. But why is it so? Why is the average voltage, or the volt second, stable? Why is it not shifting, moving up or down? And why is it keeping the voltage constant? Well, there are many ways to do it, many ways to look at it, but it is not obvious that the output voltage should be staying constant. Well, we know it is. If you feed in a certain duty cycle, you have a constant output. And again, it's very useful for the deeper understanding to ask, why is this so? Well, there are many answers that you can sort of explain it by. And here is one, and there is a YouTube video that actually elaborates on it. It turns out that you can describe the inductor as a closed loop system. Here is the difference of the voltages between inputs and output, the two sides, and then this voltage is imposing through the inductor a current, which then develops a voltage which comes back. So here it is, an explanation, one possible explanation why this voltage is actually being stable. It's not that important, really, this particular issue, but it gives you an insight in the inner working of the circuit. And obviously, this boils down to this transfer function, which this is without the capacitor, just to simplify it to a first order system rather than a second order. Another advice that I have to my students is that a good way to understand something is to explain it to others. Because if you think that you understand something, you might be missing a point. And if you're trying to explain it to somebody else, you all of a sudden find that, well, I didn't think about this, and how the hell am I going to explain it, because I have to think about it. So explaining to students one to the other, in fact, I was actually suggesting my students to, if they are wrestling with a circuit they don't exactly understand, to explain it to their girlfriend or their wife, because I think the world is simple. The world is not that complex. You don't need pages and pages of equation to explain an electronic circuit. The basics are simple, and if you can't explain it, you probably don't understand it. This is what boils down to. So again, due to the lack of time, I'm jumping into the engineering part, and I don't have much to say from other than what I've already said, just to look at the general picture here, and that the engineering work starts with specification. There is a specification, you have to design something to specification. Now, you have now many choices. There's a data sheet, application notes, reference design, papers, etc. So now comes the intuition and helps you sort of to sort out, okay, for all these things. Well, there is one possibility, it's flyback, but if this is a 5 kilowatt, you know that, well, that's not a good idea. So I'll move to another thing. This doesn't mean that you hit on the optimum solution, but it will surely optimize your time. Later on, you might have to check it, to test it again, one against the other. But the impact of intuition in the engineering work is very, very high. This is the difference, I think, between what we say, well, he is a very good engineer, and somebody who is maybe a junior and doesn't know exactly which way to go in the design. And now I'm coming to this issue of research, and it has to do with creativity. Research is something that is new, something that you develop. And I found this passage in this forum, I guess, by Carla Wolf, which I like very much, so I like to share it with you. And she's saying that creativity is the ability to produce new ideas or solutions, while intuition is the ability to understand something immediately without conscious reasoning, okay? So creativity is something new. But what is important is that they are independent. Intuition often fuels the creative process by providing a sense of what feels right, and then developing through creative conscious effort. That is, the intuition helps you to see which way to go and what is the possibility of having good result one way, or the other way, maybe not that uh, that good and not promising. And then intuition comes from the subconscious pattern, as we have said, and pattern recognition, while creativity applies this to new and novel ways. Okay, so creativity and intuition are really linked one to the other, and the higher or the better is your intuition, the better you can then create new things and use the intuition to improve them. So next, what I'm going to do is to share with you a process that I went through when actually develop a new device, and where intuition actually came in this process. Okay, so some background here, and that is I'm showing here the variable inductor that now Dr. Medini and I worked on. He was at that time a master student, but this was many years ago, like 30 years ago. And this variable inductor is built around in this particular case, a double E core. This is now the inductor. These are the DC windings for magnetization, you might say. And the idea is that when you have DC current here, it's sort of magnetizing. You go up on the BH curve, permeability goes down. So with no current, the permeability is high in the rim. With current, the permeability is low. So by the DC, then you can actually change the inductance of this unit. So you got a controlled inductor controlled by the DC current. And here's like a typical behavior. Again, this is from the original paper. But what bothers me is this coupling between the AC and these winding, because whatever you do, there is a coupling here, and therefore there is an AC imposed here. Now, the nice thing about this particular unit, which has been used, by the way, by many, many researchers, there are many, literally hundreds of papers that have used this configuration in various studies in converters and some other units. And the nice thing about it is that the polarity of the AC voltage here is opposite one to the other, and therefore the AC that you see here is low. But so you may not have high AC current, but the voltage of each one of them is high. So if you like to have a low DC current, many turns here, you'll have a very high voltage. And this sort of bothers me. What can we do about it? And this is one of the drawbacks of this unit. And here we've been playing with various configurations. And Vladimir Paperno, he is an engineer with this group here, that's a company by the name of Volta Transformers in Israel. While doing many experiments, somehow tried this configuration. And what it is the gap is here, the AC winding is here, this is the DC one. And there is nothing here. I don't know whether we forgot to put it, whatever. And lo and behold, it worked very nice. And there was no AC on this winding. Kind of very strange. I mean, what's happening here? How come there's no AC on this winding? Well, there seems to be like a transformer here. Okay. So I tried to think about it and try to explain it, that this is what I'm going to go over. But this actually was after I realized something else, which I'm going to share with you, and that is how you model a transformer. If you have a transformer, there's the input here, and here's the load, and this is now the reluctance equivalent model. We have here the electrical coupling to the unit. This flux here, which is emulated by the current. These are reluctances of these bars here. And then we have the dependent voltage sources. One is actually Faraday law, this flux affecting the voltage here and here also. And then the current is back by Ampere's law back to here and back to here. And in this case, you have a voltage coming here, and if it's loaded, then it's the current, and the current, of course, will be this voltage divided by the resistance. And here comes the intuition, and that I remembered that if you have a situation like that, which is very similar to wireless power transfer, you have two coupled inductors, the antennas, and usually it's very effective if you reflect this source into this, because this is I2, and I2 is this voltage over R. You can sort of reflect it back here, make it including the effect of this load. And when you do this, here it is, when I did it, this is now the current reflected back to this voltage source. And for the steady state and sinusoidal excitation and a particular frequency in a phasor form, it looks like that. And lo and behold, this looks like an inductor. So basically what we have here is an inductor, while the flux here is like a current, okay? So it's kind of interesting that it's another way of looking at it. Actually, it has to do with Lenz's law. I'm not going into it. And you have here this inductor, and if the resistance is small, like if it's a short, the inductance is very high. And therefore, it will sort of resist this flux from coming in, okay? So here it is. We have a situation that we can block the flux from coming in by having a short, and then the flux has to go somewhere, and this is this extra leg that we have, which has no winding on it, and it is a low reluctance path for the flux. So that's it. Here we have this high inductance, so the flux from here would prefer to go over here and not here. I have it here. Flux go this way. Magnetization will be in this path here because of the low reluctance as compared to the going through a leg with a gap. And this explains what is really going on here. So what I try to do is really to show where intuition came in. And these are these stages of understanding, and based on previous experience and knowing how things behave and where the flux, how does it move around, help to resolve this question of how the heck is this unit actually working with no DC on it. And it looks very nice. Here is an example of a LLC, which is running at constant frequency, because the operation of an LLC depends on the ratio between the switching frequency and resonant frequency. And usually we change the switching frequency and the resonant frequency is constant, while here we can keep the switching frequency constant and change the resonant frequency by changing the inductance. And here's how you have to change the inductance for various input voltages and power level. So I hope that what I just went over makes sense and understood in the way that things are happening. And I really recommend to whoever is involved in research and development to spend the time to go back and see how things evolve, because this will help for the next step, for the next time, to improve on it. And now I'm coming to the question as to whether intuition can go wrong. Well, it can. And this is a classical example here. Now, I'm showing here a flyback, and we know that due to this leakage, without a clamp, we are going to have a high voltage here, a spike, and this is something like this I just talked about in the first or second slide. So we need a clamp. And so the common wisdom is that, well, this energy now goes into this clamp. So this is the energy of the inductance, that the frequency is the power, and this power eventually is dissipated by the resistor. So here you can have this power here expressed, from which you can calculate the resistor if you decide on this voltage. Well, this is wrong. And the reason why it is wrong is because there is a voltage at this stage of this transistor being open, non-conducting. There is the secondary is conducting, and therefore there is a reflected voltage to the primary. So the current is passing through this path, and therefore there is an extra power here coming into here. So you need this extra term of the average current times the voltage to take it into account. So how can you compare with it? Well, the way is that you always have to doubt. You have always to say, okay, well, is it so? Although it looks reasonable, but here there is a unit here and the current is passing through it. So what is this current doing? Maybe it's dissipating power, or maybe there's added power, and obviously it's actually adding power here. So I think this is in general what I wanted to present here, but I like to leave you with a sort of question and something to think about, and to exercise your intuition capability. And here it is. Here is a transformer, and we are aware that we are neglecting leakage and other non-linear or non-ideal things. So we know that the flux is common to the primary and secondary, and consequently, when you divide the voltage here, this is Faraday's law, you get this ratio here. And then usually you'll find in books saying, okay, from power point of view, then the product of voltage times current on each side is mostly the same. And here it is, you got this ratio, this turns ratio, or the ratio of the current to be related to the turn ratio. Okay, but obviously the transformer does not calculate the power, and for each case calculating what current should the be delivered. There's some other process that is going on, okay? And the question that I'm posing here is, so what is this process? I mean, how is this ratio comes about, other than this general energy conservation concept? And if you look at it, it's really kind of questionable, because obviously the flux is a function of the voltage here. And then you have a current here, and there's apparently no change in the flux here. So how this current is generated? Or let's do some mental experiment here. Suppose I have an inductor, a load, and I then switch it. Obviously, when I switch it, there is a current here. That's fine. But how would the primary know that it has to increase the current if there's no change in the flux here? Okay? And I'm going to cheat a little bit here. So, you can also say that, hey, on the one hand, we have Faraday's law, so the flux is related to the voltage, and then we have Ampere law, and the flux is related to the current. So which is it? Because the current is changing. Okay? Now, there is, of course, a simple answer to that, and it's in a video that I've published in the YouTube channel of mine. But this is things that I think one should sort of test himself to see if he can really understand the simple basics. And again, it's not for the sake of actually solving questions of a transformer, but this leads to understanding other issues related to it. And again, this is shown in this, discussed in this YouTube video. So what are the conclusions of this whole story that I gave you today? That I think intuition plays an important role in power electronics teaching, studying, practice, and research. And I think it has to be taught, cultivated, and obviously questioned. So this is the end of this presentation. I guess if there are some questions, I'll be happy to entertain. Thank you very, very much for your attention.